Hi, everybody, and welcome back. We're going to have our second half of our I/O and storage session. And to start the session out, we have Bing Shi, and she's going to really kind of have a complement to Sarah's presentation from the end of the last session. But this time she's going to talk to us about a particular way to do tuning. And with that, I'll hand it over to Bing.
Hello, everyone. This is Bing Xie from Oak Ridge National Lab. Today, I'm gonna talk about our runtime I/O tuner. So, the tuner's name is SCTuner. It is an auto tuner built for HPC I/O libraries. We finished this work in collaborations with scientists and researchers from Lawrence Berkeley Labs, Oak Ridge Lab, Argonne Lab, Rutgers, and Sandia National Laboratories. So at the start, I'll talk about the full stack of scientific I/O on HPC platforms, including the specific full stack, the layers, and we'll focus more on the HPC high-level I/O library level. Specifically, I'll pay attention to HDF5. And then I'll go through about our previous parameter tuning works inside of HDF5. And in the second part, I'll pay close attention to the SCTuner, which is an auto tuner addressing dynamic I/O needs at application runtime. I'll go through about the motivations and the architecture of SCTuner, the specific benchmarking methodology we introduced, and the current status of the implementation. At the last part, I'll go through about the preliminary results of this piece of work. So scientists prefer to use libraries to manage their I/O for its portability, flexibility, and to support a variety of the data structures. So as you can see, the picture shows at a high-level scientific application usually called the high-level I/O libraries, such as HDF5, ADIUS, PNAS-CDF. They are giving the similar functions, have the tuning parameters at different levels. And it will call the I/O middleware library layer like MPI/IO. At this layer, it also has many of the tuning parameters for the optimization. And MPI/IO will call the operating system level interfaces like POSIX/IO and will communicate with the underlying file systems managed by large-scale parallel file system software like GPFS Lastre, and eventually read and write the data at the I/O hardware level. So if you look at the full stack of the I/O middleware, you can see that there are multiple layers. Each layer has several tuning parameters. It is a very large tuning space. So the default configurations in I/O libraries are obviously far from optimal. For the HDF5, ADIUS, and PNAS-CDF, they're widely used by HPC applications. They provide support for heterogeneous data and cross-platform services and high portability. And all of them have the same functionality provided to the users, is that they hide the low-level details of MPI/IO, POSIX/IO, and large-scale parallel file system softwares, and let them to manage all of the lower-level tuning parameters at the I/O library level. That is also the base we can build this work. And specifically for HDF5, it has a large set of parameter tuning parameters. For example, it has its own file format and associated with a group of tuning parameters. For example, for the file internal metadata, including the object header, B tree, etc. And also through HDF5, people can also tune the parameters at MPI level, like the number of aggregators and the buffer, the size of buffer cache for the aggregations. And for the parallel file system levels, it also has a lot of parameters to tune the data layout properties. For example, like inside of Ladder, you can tune the strip size, strip count, and starting OST, etc. So specifically for HDF5, the default HDF5 configurations are far from optimization. And for the systems such as Summit at Oak Ridge Leadership Computing Facility, and for Corey at NERSC, they have different software and hardware and with different performance characteristics, and the performance gap between the default and optimized settings can be significant. So we have no one generic solution can be easily applied or dynamically applied for all of the applications, even just for HDF5 and for different systems and for different applications. Obviously, the default HDF5 cannot fit for all of them dynamically and optimally. So previously, we did some work to identify the optimal parameters through the benchmarking methodology. We have a paper published at SCTuner Grade 2021, which is called Battle of the Defaults, which extracting performance characteristics of HDF5 under production load. Our approach is to collect a large set of repeated benchmarking results with various configurations. And we built the benchmarking profiling on top of two production HPC systems, which is Corey and Summit. And we use IOR with more than 3,000 different IO configurations, and we measure the performance of different levels, and eventually we repeat each set of the experiments for at least 100 times because of the production environment is highly variable. Through that, we identify a set of parameters that consistently provide good IO performance in the benchmarking results across platforms. These are the two observations. First is the HDF5 alignment setting is very important, and the metadata management are also crucial for overall performance. All these two observations are general and can be easily applied to different platforms, and we see the performance improvement by more than 10 times compared to the default. So here is the here is the result of the tuned performance. The left figure is the results on Summit. The right one is on Corey. So the blue box plot report the original HDF5 performance. The red one is the fine-tuned HDF5 with the profiling results knowledge built inside of it. We're reporting the time consumption, and the x-axis report the results of different application IO kernels. Here we're reporting for, as you can see, that the performance improvement from 1.1 times to 12 times, which is most significant from BPAC IO. So what we are doing inside of SCTuner compared to the previous works, which is an automatic tuning process happening at application runtime. We're motivated by different application IO that exist on supercomputers, and they're exhibiting different performance needs and IO patterns at application runtime. And the second part is that we observe different file systems have different hardware and are deployed with different file system software and configured differently. We need some automatic function to identify all of these differences at runtime and apply the most appropriate configurations inside of HDF5 at application runtime. Third part is HPC IO middleware libraries empower users to customize configurations on different layers of IO stack, but user obviously and unfortunately, because their lack of IO knowledge, they stick to the default configurations with poor IO performance. So we need the automation at application runtime to help user. We follow three major design principles. First, we want to address the different target systems. We designed a benchmarking experiment to profile the I/O behavior per system offline. Second, we want to address the I/O patterns per system. We're still similar to the previous work. We use IOR as an I/O pattern generator that covers a wide range of burst sizes and I/O scales and the different tuning configurations at the same time. Third, we want to capture the consistent behavior from noise and randomness happening under production load. We repeat the experiments and characterize the results by a 5-number summary and clustering. So as you can see, the clustering method is new from the previous works. So here is the architecture of the SCTuner we propose to realize. The first part, and the part has already done, is we want to build the benchmarking knowledge per system with a variety of I/O patterns. The second part is we want to capture the I/O patterns at application runtime, which is called a pattern extractor. We've already done that. It's built in HDF5. So the next step we want to do is based on the runtime captured specific I/O pattern and based on the profiling knowledge collected offline for a specific system, we want to know what's the best tuning parameter to determine the tuning policy and strategy at application runtime, which is the part we need to finish next. So next, I'll show some of the benchmarking methodology and the results we are having here. So first, so far we are profiling the supercomputer Summit and its file system Alpine, which is launched at OLCF and which is a GPFS file system. So inside of IOR and HDF5, we varied a number of parameters, including the number of total MPI processes, the compute nodes, the number of processes per node, individual IO size, number of aggregators in MPI and burst size in MPI IO. After we collect all of the benchmarking data, we use 5-number summary and hierarchical clustering, another simple AI machine learning methodology to further analyze the benchmarking data we have. So here is the preliminary results. On Summit and Alpine, the left figure report the results for read, the right results report the clustering results for IO writes. So it's the dendrogram figure. As you can see that I use the dot line or horizontal dot line to report how many groups we're capturing. For the read, we are capturing 6 groups. For the write, we're capturing 5 groups. And we are clustering the groups based on their similarity. If the similarity is smaller than 10 Euclidean distance, we consider they are similar. And so here are the more detailed report inside of the per clustered group, how the performance will look like. We use the 5-point statistics 5-number summary to show it. So every point at x-axis report the results of 5 points of a specific IO pattern we repeatedly performed on Summit and Alpine. And every x-axis reported a pattern result belonged to a specific group. We sorted the group based on its performance from bad to good based on its median performance. For example, if we focus on the left figure about the read and we focus on the C_0 group, we can see that the maximum point, the best performance, the blue curve of the performance is still somehow reported the lowest best performance of an IO pattern can achieve. And the y-axis report the normalized result, which means that for a specific IO pattern, we use different configurations and we see the best. We see the best from the pattern, no matter which specific configuration it used, we consider it as 1. So all of the C_0 group means that for all of these patterns, some of the configurations report the best performance as 1, but for all the configurations from this specific group, they can only achieve less than 0.25 out of 1 best performance. Definitely, some of the consistent bad, poor performance delivered by some of the configurations. We want to filter out those configurations offline and focus on the good performance ones to do the specific policy and strategy at application runtime. For the right performance, we see the similar thing. Even more good if we focus on C_4, we see that the red dots associated with that one, which report the worst performance for some specific configurations of the IO patterns, which suggests even the worst, even because some of the noise and the random competing loads compete the IO bandwidth resources with the benchmarking and experiments. Even for some worst cases, they still report more than 0.5 out of 1, which suggests extremely good performance. We want to always capture this group of the configurations and apply them at the application runtime. So here is another preliminary results we specifically break down and to look at. For example, the left figure report the aggregate data size for different IO patterns. As you can see, we are reporting the IO patterns as small as 11.81 megabyte or as large as 122.33 gigabytes. And we are looking at the specific configuration. The pattern is running on 32 nodes, and we're using specifically 8 aggregators with 64 megabyte buffer size configuration. We are looking at the specific configuration, how it performs on different IO patterns. As you can see that for these, the left figure, for this specific configuration, we can see it deliver good performance for small to medium, large of the aggregate IO patterns. But when the data size increases, it started reporting extremely low performance. Previously, as I mentioned, the higher clustering number suggests the better performance. So number 0 means the worst performance. Number 4 means the best performance. And these specific IO configuration at MPI level suggests it can report the best, consistently report the best performance for small to medium IO patterns and report extremely low performance for the IO pattern. It suggests that different IO patterns obviously benefit from different configurations. Some configurations can perform extremely good for some patterns and extremely bad for some other patterns. We need the dynamic tuning and the dynamic choosing at application runtime. So that is the preliminary results see the necessity and how the IO pattern works. And we concluded that the benchmarking analysis with controlled experiments, it can effectively capture the consistent IO behaviors under production load. And we do see the dynamism of the IO performance for different IO patterns at application runtime. And we need the automatic dynamic autotuner per file systems. And so far, we implemented IO pattern extractor in HDF5, and in the near future, we plan to realize online performance tuner in HDF5, which mainly focus on the asynchronous IO ball connector. And here is all of the talks and the acknowledgement from the support of DOE lab for different national laboratories, and the specific thanks to NSF for the support of Sudarshan Khanna. And thank you, everyone. And I didn't get the signal from Jay, so I assume I successfully finished it at the time. Thank you, everyone.
Yep, that was perfect, Bing.
Oh, okay, perfect time. Okay, good. Thank you. So any questions?
I'm not seeing any in our chat system here, so I'll get started with a few. So the Sarah pointed out in her presentation about the difficulty in trying to do any sort of benchmarking, and yet in this work you've been able to get some good results with some automatic tuning. What do you think was the key insight that allowed the automatic tuning to really work?
So it is, I would say, I'm sorry, two major parts. The challenge, I'm unfortunate I wasn't there for Sarah's talk, so I would, from my perspective, I would say the most challenging parts are two. One is what's the appropriate IO patterns should be chosen for benchmarking, which are they typical and representative for all of the supercomputer IO patterns? The second part is the high performance variability we consistently observe from the production environment. So we address this issue in two parts. One is previously in the SCC grid paper, to address the variety of IO patterns, we introduced a statistical benchmarking methodology. So basically, we look at a wide range of IO patterns from extremely small to extremely large. I think Jay also helped us to build some of what is the extremely large, right? We want it to be representative and at the same time somehow push the boundary of the hardware limitation for the supercomputers. So we look at a very large range, but we separate it in several parts. For example, in 10 groups. Per range, we randomly chosen of the numbers. So overall, we have sufficient amount of the IO patterns to give us the number that we're confident we have a good coverage of the performance. At the same time, we have the randomness per group to cover some of the runtime kind of things or the randomness from the applications. This is the first part. Second, for the highly variable patterns, we repeat the per IO pattern execution on the system to make sure that we are capturing some consistent behaviors. Yes, the third part is we really want to have some consistent behavior. That's the reason beyond of the statistical benchmarking methodology, we also use AI machine learning techniques to do the clustering. For example, am I still sharing my screen?
Yes.
Okay. For example, here, the statistical analysis, the 5-point per IO pattern, you can see that we repeat the execution and we see the highly variable difference from extremely low to some reasonable numbers. But you still can see the consistency, as I specifically point out for the C_0 or C_1 group. Each point, each line actually, each vertical line actually showing the same IO pattern with the same configuration at different times. It suggests the highly variable performance, but at the same time, it gives you consistently low best performance. Definitely something happened about the specific configuration because the patterns has its best performance somewhere else, which suggests the configuration cannot give you the best performance. Those are the tricks we're using here for the benchmarking method and for the runtime tuning, which give us the confidence it works.
All right, thank you.
Thank you.
So one of the questions that this kind of leads to is there's a lot of testing and benchmarking here to kind of feed into it. How little do you think you can get away with and still have some usable results come out?
This is a very good question and a hard question to answer. We don't have a specific number or everyone believe it is sufficient or give you the certain degree of confidence. We only based on our experience. For here, we are understanding. I think it is 120 IO benchmarks. We follow basically some of the widely used IO kernels from small to large, but we're not focusing one, we're focusing on ranges. In total, we have 120 patterns. And the second thing is because this benchmarking is built in offline knowledge, which is only the base, when we are really, when the SCTuner really works, we expect to see new patterns coming. For example, like the more machine learning or edge computing type of the IO patterns. The SCTuner can capture that, both the IO patterns and the performance at application runtime, and further feed in the offline knowledge. That is also something we plan to do in the near future. So as you can imagine, at the start, it might have very limited pool, but when you are using the tool more and more, you will expand your knowledge base. We hope that can help. Yeah.
Okay, great. And one last question. How would this work in a file for process versus like a one big file kind of environment? Is it work in both environments well, or is it really rely on those big kind of runs?
So I believe the methodology itself, definitely it is generic. It can be applied to different scenarios, to different systems, but the specific methodology is the same. You need to do the offline. You need to first identify the benchmarking IO patterns you're interested in. You need to repeatedly run the benchmark per system, and then the specific, for now, the specification of SCTuner is it is built on top of HDF5, because HDF5 somehow has the good support for the runtime tuning. And obviously, if you want to use some other, HDF5 has some of the parameters and some of the specific constraints about the files or the scenario or the environment you can working on. Later on, it's easy. I believe it is easy to apply at least the entire methodology. A specific parameter might be different, but the methodology itself can be easily applied to other platforms or the other IO libraries. Yeah.
Okay. All right. Well, thank you, Bing.
Mm-hmm. Thank you. Thank you, everyone.
All right, and now we'll go to our last talk in our session, and this is Luke Logan from Illinois Institute of Technology, and he did a bunch of work over the summer that looked at using persistent memory, and really the idea here is to look at what it takes when you have new kinds of hardware to be able to actually get the promised performance out of it. And with that, we'll go to Luke.
Now, Do I have permissions to share my screen?
You should.
Uh,
Multiple participants here. Try that.
or settings. Aye. Yeah, I don't see the option for some reason. Uh, what if I do something janky? Can I just send it to you? And
That would be kind of a long way around, but we could do that if need be.
I don't know why it's not giving me this option.
Yeah, go for it. Send it to me and I'll pull it through. It'll just
Okay.
take me a minute here. So if you want, you can go ahead and get started and just talk, and then we'll kind of catch up on the slides here.
Sure. Is my camera not working either?
Apparently not.
Goodness gracious. Okay.
Luke, if you can hear me.
Alrighty, well, I guess I'll start then.
Yep.
Hi everyone, I'm Luke Logan. I'm a PhD student at Illinois Tech. I'm a little bit congested today too, sorry about that. But today I'll be talking about the importance of leveraging specialized I/O interfaces and device characteristics to extract the full performance potential of lower latency storage technologies, such as flash storage. So traditionally, data centers have used hard drives to store data due to their capacity characteristics. However, due to the significant difference between CPU and disk performance, data-intensive applications end up getting bottlenecked by storage performance, leading to the I/O bottleneck problem. To reduce this bottleneck, fast but lower capacity storage technologies have emerged that can be used as intermediate storage tiers for applications to temporarily store data before persisting to hard drives. Each of these technologies have different performance and capacity characteristics. SATA SSDs have roughly 600 megabyte per second bandwidth and 70 microsecond latency, which is many times better than hard drives. NVMEs have about 4 times the bandwidth of SATA SSDs, but roughly the same latency because they're made from the same NAND Flash technology. Persistent memory has a bandwidth of 6 gigabytes per second with latency in the realm of nanoseconds, which is more similar to that of main memory. As the performance of these devices increases, the capacity provided by the devices decreases. Obviously, significant improvement in I/O performance can be gained by simply using faster storage devices and making clever use of multi-tiering and caching. However, simply improving storage device performance is not enough. Consideration must also be given to how data is actually stored on these devices. What's the best interface? What's the best file system? Or the best data layouts? Reusing the same methods that work for hard drives is not optimal for other storage device types. So let me see. Has the slide started?
I'm just about. I'm pulling it up now. All right. Here, let me just go ahead and get it sharing. And then,
How do I send it to webcast support?
okay. All right, so it is sharing now. So let me get down to which slide are you at?
I am on slide 5.
All right, storage characteristics.
Okay, So before I talk about the specialized storage interfaces, I'll give some background on the characteristics of different storage technologies. Next. So for hard drives, I/O requests are in the units of sectors. Typically, a sector is around 512 bytes. In other words, you can't write less than 512 bytes to a hard drive. Disks consist of multiple platters. Each platter is divided into sectors. Disks physically rotate the platters to access or modify data. This results in significant seek penalties, which is especially bad for random I/O. In addition, disks cannot process multiple I/O requests at the same time due to physical limitations, which significantly limits concurrency. Next. For Flash, I/O is in units of Flash pages, which are typically between 2 to 4 kilobytes. Flash pages are grouped into erase blocks, where each block has around 32 to 64 pages. Unlike hard drives, NAND Flash cannot modify data in place. Instead, when data is modified, the new data is placed in a separate location, and the old data is marked invalid. Eventually, invalid pages are reclaimed through a process called garbage collection. The garbage collector erases entire blocks of data from the flash device. The performance of the garbage collector is very important for overall I/O performance. Unlike hard drives, NAND flash devices have much higher I/O concurrency and lower latency. This is because there are no moving parts in NAND flash. Okay, next. The firmware of PMEM allows it to be byte addressable. However, technically, the minimum transfer size is 256 bytes, so users should be aware of I/O requests smaller than 256 bytes because they'll be amplified to 256 bytes. Thus, unlike NAND Flash, PMEM allows for modifications to be performed in place, so there's no need for garbage collection. Latency of PMEM is close to that of main memory, making it really good for small random accesses and more metadata-intensive kinds of workloads. PMEM requires users to be very careful about CPU caches, however. This is because PMEM is connected directly to the CPU, and thus I/O may get buffered in lower-level caches on the processor. Users must flush CPU caches when data needs to be persisted to PMEM, which adds an additional layer of complexity to persistent memory programming. Okay, next. So now that we've discussed some of the design and characteristics of these different technologies, I will discuss different methods to take advantage of these hardware properties. Next. Traditionally, POSIX is the interface used by applications and I/O libraries to interact with storage. The Linux kernel provides many well-tested file system implementations, such as ext4 and XFS. Most of Linux's file systems are optimized for hard drives to reduce seek penalties. However, there are file systems that are designed specifically for flash storage and persistent memory that provide significant performance improvements over typical hard drive-based file systems. F2FS, for example, is a log-structured file system designed to minimize garbage collection for flash storage. ext4 and XFS provide an option called DAX, which allows I/O requests to bypass the page cache and I/O scheduling layers, significantly improving latency. However, users must know to enable the DAX feature in order to take advantage of that. Okay, next. These are the results presented in the F2FS paper, demonstrating significant performance differences between F2FS, ext4, ButterFS, and NILFS2 over a SATA SSD. F2FS, of course, is optimized for SSDs. The other three are mainly designed for hard drives. F2FS performed about the same for the video server workload, which performed large sequential IOs, which is the most optimal IO pattern imaginable. So, of course, all of them performed about the same. For the file server, VARMAIL, and OLTP workloads, F2FS saw significant performance gains of up to 2 times over other file systems. This is because F2FS minimized the garbage collection and write amplification costs, unlike the other file systems which do not take into account the NAND Flash characteristics. Clearly, utilizing a file system designed for the particular storage device can result in significant performance benefits. Next. While selecting a file system that is tailored for a specific device can result in significant performance improvements, the file systems provided by the Linux kernel are not necessarily the best option. The typical Linux I/O stack has inherent limitations for low latency storage, primarily for NVMEs and PMEM. The Linux I/O stack introduces many software overheads that can degrade I/O performance for low latency storage. For example, the cost of context switches caused by POSIX system calls have been shown to be very costly for low latency workloads. The kernel also causes many expensive memory allocations to occur for every single I/O request. The block I/O layer of the kernel comes with optimizations to reduce seek penalties for hard drives that simply do not apply to low latency storage. All of these software costs add up and can cause significant performance loss, particularly for low latency sensitive workloads like metadata servers. Second, the kernel's I/O stack has some scalability concerns. It's riddled with fine-grained locks that can cause contention when submitting many I/O requests in parallel. In addition, hardware interrupts trigger context switches, which can also cause significant slowdowns. Okay, next. Am I still here?
Yep, you're good.
Okay. So this figure is from a work in the Usenix Annual Technical Conference that analyzed the limitations of the kernel I/O stack for low latency storage. From this figure, we can see that the kernel accounts for up to 35% of time spent in I/O for latency sensitive requests to NVMe SSDs. Clearly, for NVMe and PMEM, there is still performance being left on the table by using file systems provided by the kernel. Next. There are various interfaces and tools available that provide more performance for specific device types. SPDK is a lockless NVMe driver that completely bypasses the Linux kernel, allowing applications to interact with NVMe devices with significantly lower latency. LightNVM is a library for programming SSD firmware. For example, one can develop a custom garbage collection policy specific for their use case. DAX is a mode for interacting with PMEM that allows it to be treated more similar to main memory, which can reduce data copies and latency significantly. Of course, most application developers shouldn't be using these interfaces. Typically, you don't want your application to be confined to a particular storage device or storage architecture for portability reasons. Next. So for this reason, various I/O libraries, file systems, key value stores, etc., have been developed on top of these specialized interfaces that make better use of the devices. Application developers should consider the usage of tools with hardware-specific optimizations. There are many examples of such libraries. I've listed 4. UFS is a specialized file system for NVMe built on top of SPDK. Nova is a log-structured file system for PMEM built on top of DAX. Strata is a tiered file system that manages PMEM SSDs and hard drives using DAX and SPDK. PMM Copy is a parallel I/O library for serializing and storing data structures in PMEM that leverages DAX. So I've only listed 4 options, but again, there are many more. Next. So to demonstrate the performance benefits of utilizing hardware-specific interfaces to storage, we will discuss PMM Copy, which is a parallel I/O library for PMEM. We compare PMM Copy against other PIO libraries, which are not optimized for storing data in PMEM. Next. So first I'll provide some brief background on how different PIO libraries interact with storage. Next. Parallel I/O libraries manage the complexity of storing data structures in distributed storage efficiently. Four popular PIO libraries are HDF5, NetCDF, PNetCDF, and Adios. HDF5 has various options for laying data out in storage. The contiguous data layout shuffles data so that data is stored physically in order. This results in significant data copying and networking costs that are not the most efficient for PMEM. The chunked layout divides datasets into fixed size chunks and stores each individual chunk, which avoids this shuffling cost. NetCDF and PNetCDF are both very similar to each other. They both store data using contiguous data layout that is similar to the HDF5. The main difference between the two is that NetCDF is implemented on top of HDF5, whereas PNetCDF is an entirely separate implementation. Lastly, Adios unifies the different I/O transport mechanisms, HDF5, MPIO, POSIX, etc., under the same interface. In the POSIX and MPIO modes, Adios stores data independently per process without any data rearrangements, so that avoids the networking and shuffling cost of the contiguous layout policy. Okay, next. So now I'll provide some more insight into how the DAX mode for PMEM is used. Next. DAX allows applications to interact with PMEM more directly, bypassing page caches and other layers of the Linux stack. DAX can be leveraged using two interfaces, either POSIX or memory map. When using the POSIX mode to interact with DAX, the Linux kernel will avoid different layers of the typical stack to reduce software overhead. This option, of course, still incurs other software overhead such as context switching and memory allocations. The memory map interface allows PMEM devices to be treated simply as an array of bytes. This avoids the kernel stack entirely. Below are two small examples of interacting with PMEM. An ext4 file system is mounted in DAX mode on /home/loop/pmem. In both examples, a file called hi.txt is created on the PMEM device using the OpenSys call. In the left example, the user writes 100 integers to the file using the write system call. In the left example. In the right example, the user maps the file and treats it as an array of integers. The user then writes data to PMEM as if it were main memory. Okay, next. Now I'll discuss the design of PMEM Copy. Next. So we'll start with a small use case example for PMEM Copy. In this example, we show how to use it for writing a 1D array of 100 doubles per process. The first 12 lines initialize MPI and a few variables. Lines 13 through 16 are the actual PMEM Copy API in use. PMEM.mmap memory maps part of the PMEM device. PMEM.alloc is used to allocate the array, and PMEM.store is used to serialize a portion of the array into the file. Next. So PMEM Copy fundamentally assumes that every compute node is equipped with a local PMEM device, which can be used to store data. PMEM Copy will place data directly into the PMEM local to the compute node using DAX. It will then trigger an asynchronous process to take care of flushing the data from PMEM to the parallel file system and the burst buffers. Okay, next. Typically, when serializing a data structure, a parallel I/O library will serialize that data structure into another DRAM buffer and then copy it over to PMEM using POSIX. However, by using the POSIX API to interact with PMEM, an entire unnecessary copy of the data is made, which can significantly reduce I/O performance. Unlike other PIO libraries, PMEM Copy utilizes a special DAX memory mapping interface. This allows PMEM Copy to serialize data directly into PMEM, avoiding an entire copy of the data. A similar data copying cost is also avoided when deserializing. Next. So to evaluate PMEM Copy, we ran two workloads, the S3D combustion code and an analysis of what that code outputs. S3D will write a 40 gigabyte 3D rectangle to PMEM. The analysis code will read that 40 gigabyte rectangle from PMEM. Each process performs an equal amount of I/O. Okay, next. So we ran all of the experiments in Chameleon Cloud on a Compute Skylake node. The Skylake nodes come with 192 gigs of RAM and a total of 24 cores and 48 threads. We didn't have access to PMEM, so we emulated it using the approach in the Strata file system paper. We used Linux's emulator to treat 80 gigs of DRAM as PMEM, and we used timers to make the DRAM have similar bandwidth and latency characteristics to PMEM. Okay, next. So in this experiment, we compared Adios, NetCDF, PNetCDF, and PMEM Copy for the write-intensive workload. PMEM Copy is configured to use the same serializer as Adios, the binary packed serializer. As the number of processes increases, we see that the benefit of PMEM Copy gets higher. From these figures, we see that PMEM Copy A performs up to 15% faster than Adios by avoiding data copies caused by POSIX, and up to 2.5 times faster than NetCDF and PNetCDF. This is because NetCDF and PNetCDF shuffles data around before placing it in PMEM, incurring significant data copying costs. Okay, next. In the case of the analysis code, we see a similar trend. PMEM copy A is 2 times faster than Adios and 5 times faster than NetCDF and PNetCDF. The performance gap here is more severe because reads are a lot faster than writes to PMEM. Okay, next. So in summary, we have shown that existing PIO libraries introduce significant overhead when interacting with PMEM due to data copying costs. This was caused by the fact that they did not leverage PMEM's special memory map interface. We found that by leveraging this, PMEM copy can improve writes by 15% and reads by 2 times over other PIO libraries. Okay, next. And next. So the main takeaway of this talk is that you should utilize libraries and tools that take advantage of the specific hardware interfaces and characteristics of the storage you're using. Overall, we discussed the design and characteristics of different storage technologies. We've identified various interfaces and tools that can leverage the characteristics of these different technologies. And lastly, we've demonstrated the performance benefits of utilizing hardware-specific interfaces to storage through PMEM copy, and found that I/O performance can improve by as much as 2 times over unoptimized approaches. Okay, that concludes my talk. So thank you all for listening.
All right, thank you, Luke. We don't have any questions that I'm seeing, so I will start and say what you showed was pretty clear that by using the proper hardware driver interfaces for the specific devices that you have can make a huge difference. We know this is true for PMEM, as you've demonstrated. Now, what about other kinds of storage devices like SATA-based SSDs or PCI Express-based NVMe devices or things like that? Do they have other special interfaces that we should also take advantage of?
Yes, NVMEs, for example, have SPDK, which is a driver that is much faster than what Linux provides. For SATA SSDs, I don't think there's really anything available outside of specific file system implementations provided by the kernel. F2FS, for example, provides data layout policies that are much more optimal for SATA SSDs than ext4 and XFS. So there are options available to you that are faster for SATA SSDs.
All right, so is there a way to determine whether or not the software that you have is getting the right advantage of the hardware that's underneath?
Benchmarking is probably the easiest way to determine if you're getting the full potential of your hardware. The device manufacturers report bandwidths that should be very close to what you get. So if you benchmark your device using the special IO library or the special interface that you're using and you're getting really close to that peak bandwidth, then you're doing a good job.
Okay, so for Sarah's talk earlier today, she was talking about a lot of the difficulties in trying to get reasonable benchmarks and a lot of the challenges with all the different software layers. Where should somebody, if they want to try to figure out if they're getting reasonable performance, what kind of layer should they come in at to be able to see if they're getting close to their potential peak?
If you have cool storage devices like NVMEs and PMEM, SPDK is as close as you can humanly get to the hardware. It's literally the driver. And for PMEM, of course, there's DAX, which physically maps the PMEM device into your application. So if you have those two devices, that's probably you can use those special interfaces to get pretty darn close to the hardware.
Okay, so I think I was asking a slightly different question, but if you how do you make sure that the libraries that you have installed, in other words, what can you look at in terms of a configuration to see if the software has been optimized by your system administrator, for example? Is there any kind of clue that you might be able to get?
Probably, I would probably say that you should have some idea of how your application should perform. If you're seeing that it's crazy slow, or there's something like your performance is fluctuating crazily, then that's probably a good sign that there's something wrong. But I don't know of any specific tools or methods to say that this certain setting is optimized. That probably depends more on the specific thing that you're using.
Mm-hmm. So one other thing I know you've looked at, and we've talked a bit about, is there an optimal device from a price performance standpoint as far as you're concerned?
From what I can see, NVMEs are definitely better in terms of price per performance than SATA SSDs. The gap between those two is closed pretty significantly. You can get 4 times the bandwidth of a SATA SSD for only like 60% more money. Mm-hmm. Now, of course, it's you get a little bit less capacity, but you get a lot more performance out of NVMEs than SATA SSDs, and you get so much more customization out of it too.
And what about PMEM?
PMEM? Yeah, no, PMEM right now is very new. In terms of price per gigabyte, it's actually the same as DRAM, but it has a lot more capacity, so you're just paying a lot more money for it. And so yeah, in terms of financial cost right now, PMEM isn't, I wouldn't say it's the most financially safe decision to make.
Right. Okay. So where do you think is the next place to go? Because I know you've mentioned the different optimizations that happen at different levels in the Linux kernel. Is there a way that we can eliminate the need of the applications to have to put in these custom device support by doing some changes to the Linux kernel?
So you can definitely improve the kernel IO stack significantly. Like, for example, you could just build a different IO stack and just rip out Linux's device drivers. That's certainly possible. But for the most part, editing things within the kernel is very difficult. So I would say it's probably better just to redo it.
All right. And with that, then I think we will end the session here. So thank you very much, Luke.
All right,
And
thank you.
And thank you to all our speakers. And with that, we will conclude our IO and storage workshop. And thank you for SagePC for hosting us, and hope you all got some good information out of this. I enjoyed presenting it. I hope you enjoyed listening. All right. Thank you for coming.